Hey guys, welcome back to another computer science lesson. Last week we did ASCII and Unicode, and don't forget, like, the difference between ASCII and Unicode is that ASCII you cannot have many characters. However, your file size is much smaller, whereas Unicode you are allowed a lot of characters, 65,536 if I remember, but the file size does get bigger. Today we're going to be looking at images and compression. So I've got an image here on the screen. Pause the video, have a think. How do you think this image could be coded? So all of the images on the computer that are sent over the internet, everything on a computer is all in binary. So how do you think that we could send images or display images? Well, the answer is that we have pixels, and they're divided into little squares inside of the image, and they have a binary code behind them which represents their color. So this is a black and white image just here, and I have it's been broken down into, I think, 100 pixels, and there's a 0 which represents white and a 1 which represents black. And so that's how an image is coded. So there's binary codes behind each pixel, and then the colors displayed based on what that binary code is. So the pixel, images are made up of many pixels. A pixel is the smallest identifiable area of an image. Pixels are arranged into rows and columns, and a pixel is a single point in a geographical image. So if we just zoom in on this image just here, you'll see like all of these little squares. These are pixels. They are very, very minute, and your screen is made up of thousands upon thousands upon thousands and thousands and thousands of pixels. So can you please write down these 4 bullet points and then come back? So resolution is made up, is basically how many pixels are within a specific area. So for example, on your TV, it's 192 times 1080 if you have a HD TV. And so that's the concentration of pixels that you can see. And the more pixels you have, the higher the quality of the image. So I've got 2 images just here. 300 dpi, that basically means dots per inch, which is basically pixels per inch, ppi. And you can see like there's 300 pixels per inch here on this image, and it looks quite good quality. Here there's only 72 pixels per inch, and the quality is really reduced. So the higher the quality of the image, that basically means that there's more pixels there to have that higher quality. So can you please pause the video and write down these 3 bullet points as a definition for resolution? And can you also write down dpi equals dots per inch and ppi equals pixels per inch? The same thing. So when we create an image, as I was saying, each pixel is given a binary value. Each value represents a different color. Using 1 bit per pixel, so that basically means like a 1 or a 0 per pixel, allows only 2 values, 0 and 1. There is cases though where you can have 1 is white and 0 is black. It depends on what question the exam board can give you. And so if they ask you to color in an image, then you need to have a look at the key what the exam board give you. These images are also referred to as bitmaps because basically it says what's behind each pixel. It maps out each pixel as to what color it is, hence the term a bitmap. So again, can you please copy down these bullet points just here? I'm sorry guys, there's a lot of notes in this lesson today. Okay, so black and white images, we know there's a 1 or a 0 behind each pixel. But what about when we've got colors involved in an image? Well, we've got a 1 for white and a 0 for black. We can't add any more colors to represent a certain bit combination. So what we have is we have more bits per pixel. So instead of like a 1 for black and a 0 for white or something like that, we could have 2 bits per pixel, which would represent 4 colors. You could have 0 and 1, which could represent blue, 1 and 1, which represents red, 0, 0, which represents green, and 0, 1, 0, which represents yellow. So you can have combinations. The more combinations of bits per pixel, so the higher the amount of bits per pixel, the more colors you can have. So for instance, here, 4 bits per pixel, you've got 16 different combinations, so therefore you can have 16 colors. This image I've got just here, this has 8 colors, so behind each pixel is 3 bits. So you could have like 0, 0, 0 represents white, 1, 1, 1 represents black, and then you can have, I don't know, 0, 1, 0 represents this light blue just here, and then 0, 1, 1, 1 could represent this color, and so on and so forth. So the more colors you have, the higher the amount of bits per pixel. This is called color depth. So how many bits for 256 colors? Well, notice this is doubling up. So 5 bits would be 32, 6 bits would be 64, 7 bits would be 128, 8 bits will be 256. So 8 bits per pixel. If you have 8 bits per pixel, you can have up to 256 colors. So what we use today, the present standard is 24 bits per pixel today. And this means that each pixel consists of 24 bits with 8 bits used for each color, red, green, and blue. So everything you see on the screen is actually tricks you. It's basically behind a pixel on a screen, you have red light, green light, and blue light, and these merge together. And your brain thinks, oh, right, that's orange, even though like it's only showing a bit of red light and a bit of green light and stuff like that. So this is basically, it's the variation. You've got 256 variations of red, 256 variations of green, 256 variations of blue. These combined together, you can produce over 16.77 million colors, which is absolutely amazing. So this is called color depth. If you've got 24 bits per pixel, you can have up to 16.77 million colors, which is really good. So let's get down some notes on this. Can you please write down more bits per pixel equals more color combinations, and then write this down here. So pause the video and then come back. Now, to calculate color and how many colors that there are, or how many bits per pixel that there are, we need to look at our binary columns. I'm sorry, the handwriting isn't great here. I've written it out on paint. So here, let's say I've got 16 colors and I need to figure out how many bits per pixel. Literally, you can just look at this image here and remember this image. Remember that you should remember your binary columns anyway. And just above the binary columns, just do 2 to the power 0 and then count all the way up. If you remember that, then you're going to be fine in calculating this. So here I've got 16 colors, and that equates to 4 bits per pixel because 2 to the power 4 just here. Let's say I've got 32 colors, that's 5 bits per pixel because 2 to the power 5 is just here. Let's say I've got 2 bits per pixel. Well, I can just look at this top row up here and say, oh, it's 4 colors. Let's say I've got 7 bits per pixel. Oh, there's 128 colors that I can choose from. Let's say I've got 87 colors. Now, 87 lies in between here. We just round up and we say, well, it's 7 bits per pixel. So literally, guys, let's say I've got, well, have a think. I've got 38 colors. How many bits per pixel do I need? The answer here is 6 bits per pixel because 38 lies in between here. All right, let's say I've got 17 colors. How many bits per pixel do I need? The answer is 5 bits per pixel because it lies in between here. Let's say I have 200 colors. How many bits per pixel do I need? Well, 200. The next number on from this will be 256, so that would be 2 to the power 8, so it'd be 8 bits per pixel. Let's go for, I have 5 bits per, I've got 6 bits per pixel. How many colors do I have? The answer is 64, because 2 to the power 6 is 64. So I hope that's okay, guys, and I hope you can figure out how many bits per pixel you can have based on the amount of colors you've got. Can you please pause the video? This is really important. Color depth equals amount of colors. The higher the color depth, the higher the image quality. So the more colors you have and the more variations of that color you can have a much, much higher image quality. If it's rich in color, then you've got a great image quality. All right, so pause the video. Can you please copy down this little image just here, and this sentence underneath at the bottom, and then come back. Okay, so to calculate a file size of an image, what we do is we times the width by the height by the BPP, which is the bits per pixel. So here in this image, well, pause the video and calculate the file size of this image using that formula. And also, can you please copy down the formula? Okay, so I hope you found that okay. Basically, here, let's have a look at the width. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we've got 10 for the width. Let's figure out the height. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we've got 10 for the width, 10 for the height. How many bits per pixel do we have? Well, we have 1 bit per pixel. So therefore, it's 10 times 10 times 1, which is 100 bits. And what we like to do is we like to convert it into bytes where we can. So 100 divided by 8 is 12.5. So this size of this image is 12.5 bytes. Okay, guys, so to make a file size smaller, we use compression. And the advantages of compression are there's less disk space used. So imagine I've got a file size that's, I don't know, 10 gigabytes. And I don't have 10 gigabytes space on my hard drive. If I compress that file to 1 gigabyte, I'll be able to save it on my hard drive. It also saves money as well because imagine on a big scale in business and you've got billions and billions of files and you need to buy server space in order to store those files. If you can compress them down, you'd have to buy less server space, which would save your company money. Also, it's faster writing and reading. So when you open up the file and you're ready to go, it will open up quicker and you'll be able to write that file quicker and save it faster. Faster file transfer as well. Say you're sending that file across the internet, then you are basically you're sending a much smaller file across the internet, so it's going to send faster across the internet. Also, because you're sending it across the internet, there's less amount of packets to send over that internet, and then therefore there's going to be less data collisions. Now, a data collision is basically when two packets of data go poof, collide and go corrupt. Now, you don't want data collisions because then you're going to have to resend packets, which makes it much slower. So the less amount of packets you send in, the less amount of chance you're going to have a data collision, therefore it can send faster as well. So there's loads of advantages to compression. I need you to remember all of them, if you can. So can you please copy down this entire slide and draw some little pictures next to each bullet point. This will help you remember it. It's a nice little revision technique. So pause the video and off you go. Okay, so there's two main types of compression I need to teach you, and that's lossless and lossy. Now, lossless compression makes file size smaller without losing any quality. So for instance, let's say I need to make a load of a text file smaller. I would use lossless compression because it doesn't lose anything. You don't lose anything by doing it. So you don't actually remove characters, you don't remove spaces, you don't change stuff that can affect the quality. And this is used on books, code, medical scans, because in a medical scan, let's say you've got an image of an X-ray, you need that image to be perfect. You cannot lose any quality in that image. So for instance, let's say that you're looking for little white dots in the image, and because you've shortened it down, it removed those white dots, then you wouldn't have an accurate image. So you need medical scans to be the perfect image without losing any quality whatsoever. Code, if you compressed down some Python code, for instance, and it removed some colons and brackets, your code wouldn't work. So you have to use lossless compression. And same with books, your book will be unreadable if you were removing text from a book. So lossless compression is used for these kind of things. It makes a file size smaller without losing any quality. An example of where this could be used is the RLE algorithm. This stands for run length encoding. It basically records a number of consecutive pixels in the same color, or strings in repeated strings or repeated characters in a string. So for instance, here we have an image, well, a line of an image of pixels. We've got red, blue, 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 blue. In the image line above, it could be 3R7B as opposed to RRR B B B B B B B, or I mean, here, guys, it would actually be the binary value of 3. It would be the binary value of that code for that image, for that pixel. Sorry, it would be the binary number 7 and the binary value of blue for that image. With the RLE, no information is permanently lost, therefore it is lossless, because when you want to decompress this line in the image, you just go, oh, right, okay, I need 3 reds and 7 blues in a row, done. Nothing's lost, nothing's changed, you haven't lost anything at all, that quality has been retained. Another example is here with characters in a string. You've got 4 A's, 5 B's, 7 C's, and 1 D here. So what you do is you just say 4A, 5B, 7C, 1D. Now let's have a look at another example. RLE is good when you have long runs. If you do not have long runs, you could make your file size larger than the original. So for example here, there's no runs of data. It's just AB, 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 and so on. Now the size of this string is 14 characters. If it's saved in extended ASCII, which is 8 bits per character, the size would be 14 bytes. So the size of this string just here is 14 bytes. Now the RLE algorithm would convert it to this 1A, 1B, 1A, 1B, 1A, 1B, 1A, 1B, and so on and so forth. The size of this string is now 28 bytes, which is double the size. So it's not very good if you don't have long runs. If you have long runs, it is really, really good. Now, why probably thinking, well, why do I need to put 1A? Can't I just put A? Well, the algorithm needs to be consistent. At the end of the day, the algorithm, when you decompress, it looks for the first part here, which is the number of how many characters or pixels that there are. And then the next part is the character or the pixel. So that's why you put 1A instead of it just standing on its own. Okay, so now it's time to get down some notes. Can you please summarize the RLE algorithm for me? This could be either copying down the entire 2 slides, this one and this one, or you can put it in your own notes. And I need an example down though. And so pause the video, write down about the RLE algorithm, and then come back. All right, so the next type of lossy compression, is lossy compression. So Lossy uses an algorithm to permanently remove unnecessary data to make a file size smaller. So this time, instead of making it smaller and keeping that quality has actually been taken out. This could be like, say, if you've got 2 different blends of blue, you just say, right, okay, we're just going to have the standard color blue instead of 2 different blends. Now, this reduces image quality. It can reduce sound quality. It can reduces quality, basically. It's used on videos, images, audio files where you don't have to keep that quality there. So, for example, if like you're doing a YouTube video, it doesn't really matter whether it's in HD or it's in 720p. So you can use lossy compression on that. With random photos on the internet, it doesn't matter because that quality doesn't have to be rich or the same. It's not going to be decreased to a point where it's unreadable or unusable or you can't watch the video. It's just going to be a smaller with less quality. So you can take the color out, decrease the color depth. You can remove sound, so humans can't hear. So for example, MP3s, what that does, humans can only hear above 20,000 hertz. Below 20,000 hertz. If you've got sounds that are above 20,000 hertz, humans aren't going to hear it anyway, so you can take that out of the audio file. You can remove pixels. So for example, this screen of me right now, if you remove pixels out of that, it'll be less quality, but you'd still be able to see me, you'd still be able to see what I'm doing and stuff like that. So can you please copy down this entire slide? Cheers. All right, so now we've got an exam question. That's the end of the lesson today. I've gone through a lot of core learning in a very short amount of time. So we've got some exam questions to wrap up our knowledge. Xander's tablet computer comes with system software, including an operating system and utility software. The utility system software provides compression software. Xander uses this to compress an image. Explain how compression software will compress the image file. So here you need to say different types of compression, how it will compress the file, and also the advantages of it. It is a 4-mark question. Oops, there, 4 marks. So please answer the question and then we'll go over the mark scheme. Okay, so here's the answer. Now, I want to start getting you into this early on how OCR mark papers. Basically, you get a mark per bullet point if you said various bits and bobs. So you get a mark saying use an algorithm, and then to remove unnecessary data or repeated data. You get a mark for saying this could be lossy or lossless. And then you get a mark for explaining about lossy and lossless. You can't just literally say, do lossy and lossless, makes file size smaller, send it quicker across the internet. You need to be explaining why your answer and much more detail on how the answers come about. So lossless will not remove data permanently. Lossless means original file will be restored. Lossy is permanent deletion. It could be done by reducing the amount of pixels or record the change in the color for each pixel instead of the color itself. Run length encoding, you could have used that in your answer. So you could use run length. An example of lossless compression is run length encoding. This is used to record the number of consecutive pixels or of that color instead of every single pixel. You could have also said with lossy, you can decrease the color depth. So basically, trick is, guys, give an overview. So say use an algorithm to remove unnecessary repeated data. An example of this could be lossy or lossless. Lossless will not remove data permanently. Lossy is permanent deletion, and then go through some examples of each one. That's where you'll get the 4 marks. And throughout these next 2 years, you really need to be explaining your answers in detail and depth. All right, so I've got the next question. Kofi uses his computer to record an audio file of himself playing his guitar. He emails his recording to a record label. He uses lossy compression to produce a music file. Explain 2 reasons why using lossy compression is beneficial. So before you start this question, it's 4 marks. So that's 2 marks per point. And basically the best tip I can give you is so what? All right, it makes a file size smaller. So what? What's the impact of making that file size smaller? How to make a file size smaller? What's the beneficial of using lossy as compared to lossless? Answer the question, and then we'll go over the answer. Okay, guys, so the answer. Lossy means the decompressed file is not identical to the original. The difference is unlikely to be noticed by humans. This is a great benefit, and this answer key is really small because there's loads of benefits of lossy compression. All right, so the next one is lossy will decrease the file size. Now here it's so what? What's the impact of this? He's emailing his recording, so therefore he's sending it over the internet. So the impact would be that he could send it quicker over the internet and have less data collisions, and well, less chance of data collisions. And so it can be sent via email because emails have like email caps and stuff like that. If you said to reduce disk space, you wouldn't get the mark here. But if you did say like to reduce disk space on the person's computer when saving it when it's arrived over the internet, great, it would do, because he said in the question that he's sending the guitar recording over the internet. All right, so I hope that makes sense. Always so what it. Never say a statement, explain why that statement is a benefit and an advantage. All right, last question. The website of a school allows visitors to download JPEG, MP3, MPEG, and PDF files. The video clip is compressed using lossy compression. Explain why lossy compression is suitable for a video clip, but not suitable for a text document. So again, this is 3 marks. So answer the question and then come back. So here the answer is, as I was explaining, when the file is compressed, some detail/data or quality resolution is lost, which is not noticeable in the video file, or video can still be viewed but with a lower quality. But if you reduce a text file with lossy, it makes it unreadable because you lose text. So that's the answer, guys. I hope that's all makes sense, and I hope you now have a much more in-depth knowledge of compression. If there's any problems at all, please do email me. I know it's quite hard to get your head around at first. We will be covering this when we go back as well. But it's really good to get your head around this now and build those foundations, and then we can come back to it at a later date. Next week, we've got a quiz out for you, just to basically test your knowledge on what you've learned this module and see where you're currently at and what we need to address next year. So please do have a bit of revision and then answer the quiz for next week. All right, thank you very much. Have a wonderful rest of your week. Cheers. Bye-bye.